Alright, I'm continuing to make my way through Fire in California's ecosystems. I'm on Chapter 4. Main thing I was reading about today was all about ignitions. So diving into where ignitions come from. Hint, hint, it's mostly humans. But it also started getting into lightning, and I'll talk about that throughout the course of this video. Before I get into that though, there was one section that was talking about wildfire models, and it just reminded me of some of the work that I was doing when I was a graduate student earning my master's in meteorology at San Jose State under the Fire Weather Research Laboratory. And I just want to talk about the model that we run out of that lab because it is honestly amazing. And then we can also talk about some of the other technology that has been quickly advancing in the world of wildfire and why that is a good thing, but also a bad thing. So this model we have at the Fire Weather Research Laboratory, or it's actually called the Wildfire Interdisciplinary Research Center now, because it's no longer just fire weather. We've brought in different experts from all kinds of different fields: ecology, modeling, sociology, kind of have the human aspect as well. So it's Craig Clements is kind of the director of this lab, and he's basically just been picking off wildfire experts in all sorts of different fields and bringing them under one roof. And one of the best things that this group has been able to do is create what's called WRF-S-Fire. It's the wildfire model that we run out of there, and how it works is it basically takes every single wildfire factor you could think of: temperature, wind, humidity, slope, elevation, fuel moisture, what kind of fuels you're talking about. And then it takes your fire perimeter and where you have the active hotspots on the fire, and then it uses all of those variables and the forecast of those variables to forecast how the fire is going to spread over time. So using the fire behavior triangle: fuel, weather, topography, and the flame itself, it has a pretty kind of, I was about to say a beautiful simulation, because it actually is pretty amazing when you see how it actually will have it move through the topography, and it shows you exactly where the flames are going to go. And again, this is still relatively new, but in the times that I've used this in wildfire forecasting, it's been quite accurate, surprisingly so, I would say. And what's maybe most amazing about this model is it also takes into account how the wildfire creates its own weather, and then how that will then impact the fire spread. That's something that really brings this model out of the pack and makes it, I'd say, special, you could say. So that's pretty amazing form of technology. We've also seen huge advancements on the wildfire side of things. Some of the aircraft they're using these days, night vision goggles. We're using satellites to be able to figure out exactly where on the fire it's burning the most intensely and to know exactly what intensity it is burning at, almost in real time. The one that was interesting that I heard the other day, we actually ran a story about this on the news, is we now have hundreds of cameras set up all over California, and with those cameras we're using artificial intelligence to be able to spot when smoke is coming up on a hillside, and then it automatically alerts authorities. So they're able to get crews on that fire way faster than we could have in the past. We would have needed, well, we did have fire watchers throughout the state, or fire spotters, but now we have hundreds of fire spotters popping up every single year that use artificial intelligence to spot these fires almost instantly. So that's pretty amazing. So how could these advancements be good but also bad? So it could be good for obvious reasons. You spot a fire, you put it out before it gets big. Seems good. You have a wildfire model that shows exactly where the fire is going to go, so you know exactly where to put in some containment lines, how to strategically move resources around to fight that fire. That definitely seems like a good thing. How it could also be a bad thing, though, is over the last 100 years, we had a history of fire suppression in California, and it was part of this war on wildfire that started in the early 1900s. There were some really bad fires up in Montana and Idaho, and ever since then we're thinking of wildfire as the enemy. So the second a fire pops out, put it out as quickly as possible. I believe there's even a policy of have all fires out before lunch or something like that. But what happens is the California ecosystem naturally needs fire. In fact, a lot of our plants evolved with fire and can't survive without fire, as we've seen with some of the giant sequoias where fuels accumulate around them, and then the sequoias that would have been fine in some slow burning fires that come through every 5 years, all of a sudden the fuels accumulate, and then you have a huge fire that comes through every 40 years. It overwhelms the sequoia's natural defenses, and then the tree ends up dying when it would have been fine in the past. Cutting to the chase there, with fire suppression, fuels build up, and that leads to more extreme and larger, more dangerous wildfires in the future. So as our ability to suppress fires gets better, we run into the danger of actually creating more danger. So kicking the can down the road, you could say, even more so than what we could have done in the past with our previous technology. So maybe things will just be balanced out because as things get warmer and drier, we're already seeing worse wildfire activity. So maybe that we're just keeping pace with wildfire as it gets worse. But a big part of the reason it's getting worse is because of all of the fuels that have accumulated. So we're really just making that part of the problem worse. So that's something that I'm going to continue to think about. I think the answer might be the fact that we understand that we do in fact need fire in California. So maybe we use that model out of San Jose State to show that the fire is going to burn today, but it's actually not going to threaten any structures. So maybe we don't even need to put it out. Maybe we don't need to spend millions of dollars to put out this fire that's burning in the middle of nowhere, and the model is showing that it's not going to get out of control over the next 48 hours. So we can let the California ecosystem naturally do its thing. Now that's not saying just let all wildfires run wild. We would continue to watch them and suppress them when necessary, but with our advanced tools, we might be better able to just watch them instead of putting them out instantly. So that could end up helping our wildfire problem. And you could do the same thing with prescribed burns. You could put down kind of a little what your prescribed burn plan would be, put it into the model, see if the model's showing that it would get out of control. If it's not, then you go forward with the burn. If it is, maybe that's one of those days where it would turn the public against prescribed burning, so that's one of the days you don't do it. I know they already do a lot of fire forecasting with things like that, but it's just as our technology advances, it may lead to some good things in the future in terms of using fire to our advantage. So that was just a little side note and a tangent of something I was thinking on. One other thing before we get into ignitions is in my last video I was talking about fuel moisture, and this is important for our talk about ignitions, but I just wanted to go back over it really quickly because I was talking about the different categories of fuels. You have 1 hour fuels, 10 hour, 100 hour, 1,000 hour. 1 hour is going to be your very fine fuels, 1,000 hour is going to be your very large fuels. I always say 100 hour, you could think of a fuel about the size of your wrist. And what those hour increments mean is how long it takes for that fuel to respond to the moisture in the environment. So your very fine fuels have a large surface area to volume ratio. I know that's getting a bit sciencey there, but that means you just have more surface with that fuel, so it's going to be interacting with the environment more than the log, which most of that log is actually in the middle. It's not on the surface. So every single day, or not every day, but most days, your temperature goes up in the afternoon, then it goes down at night. And your relative humidity is going to be opposite. Your relative humidity goes down in the afternoon as your temperatures go up, and then it goes up at night. And you have that diurnal pattern for both of those. And you can also see this with some of your fuels, but it's going to be on a time lag. And the larger your fuel is, the longer that time lag is going to be, because it takes longer for the larger fuels to respond to the environment around them. So let's say you see your fuel moistures drop. On your 1 hour fuels, you'll see them drop just in a very similar way. So the fuel moisture, the amount of moisture within the fuel, it's well named, that drops in a very similar way to your relative humidity, but just with a little bit of a time lag. And then, not a big surprise, but with your 10-hour fuels, you see that drop as well, but it's going to be with a larger time lag. And then with your maybe 100-hour fuels, you're not going to see as much of that diurnal pattern. You'll just notice a steady decrease if you have maybe warm, dry conditions moving in. So just wanted to go back over some of that information because that's one of the most important concepts, I think, to understand in terms of wildfire danger, just because, I mean, my own master's thesis showed that 100-hour dead fuel moisture is the best predictor for extreme wildfire days, and especially when we're beneath that threshold of 10%. So, talked about fuels, we've talked about technology. Within technology, remember I mentioned how we have AI cameras that can spot fires popping up. What you're looking at there is fire ignitions. So now let's transition into talking about fire ignitions. Now you've probably heard this fact, and I don't actually know the exact fact, but I've heard some different numbers out there. The large majority of fires that we see are started by humans. I've heard between 80% and I've also heard 90% are started by humans. And the best plot that I've ever seen that explains this perfectly is it shows your fire ignitions, goes up throughout the summer, comes down into the winter, just because you might have all the different sources for ignitions throughout the year, maybe in steady numbers. But then you need a lot of things to come together for the ignition to actually happen. Your temperature has to be right, your fuel moisture has to be dry, how densely your fuels are packed, what kind of fuels you have, what is the source of ignition. All of that has to come together for the ignition to happen. So that's why you see a lot more ignitions happening during summer. You have more of those factors all aligned. But this plot that I was talking about, that just perfectly shows that humans are kind of the problem when it comes to fire ignitions, is it shows us going up during summer, and then right around 4th of July, you see this massive spike, and then it comes right back down, and then we just continue our track throughout the summer. It's just a huge spike on 4th of July. Obviously, that's from all the fireworks that are happening. So that's one of the things that could start a fire. Fireworks, maybe throwing a cigarette. I've heard a couple other ones that are very common. Dragging chains behind vehicles. A lot of fires will start in the grasses right around highways. I believe it's for that reason. Or my cousin, who's a firefighter, he said that most of the fires they see are from catalytic converters, which is interesting. And you can just imagine there's lots of other ways humans start fires. You make a campfire, you don't put it out completely, those sorts of things. And the number of ignitions increases as more humans move into the wildland-urban interface. So I threw out the number, maybe 80 to 90% of ignitions happen because of humans. The remaining, let's say 10%, is mostly going to be from lightning. But what is interesting is most lightning strikes don't lead to fire ignitions. Most lightning strikes, actually, there was a study in 2016 that looked at over 2,600 lightning strikes in Yosemite, and only 1.4 of those actually led to fires. Now, there could be some problems with that data because maybe there were some fires that started but just stayed really small, so they didn't account for it. But even if you round up to 5%, that's still a very small number of lightning strikes that actually end up leading to fires. And then a large percentage of those are just going to remain small. But in order to understand where these ignitions would be, we first have to explain how lightning forms. So typically in California, we're going to get lightning when you have moist, warm air being lifted up. Because as it's lifted up, it cools down, it condenses, you get some clouds, you get a thunderstorm, and then if we really want to get into the science here, as it's condensing, it's warming up the air around those liquid droplets because it's the opposite of sweating. So when you sweat, you have a liquid droplet that evaporates and that takes energy from the environment and cools down your body. That's why you sweat. But in the cloud, when it's condensing, it releases energy into the environment, makes the air around it warmer. That warm air is less dense, so then it rises. And that's why your thunderstorms grow so tall. And then they'll have that anvil shape, I believe, when they get to the top of the troposphere. They kind of flatten out up there. So that's the science behind what's going on with the thunderstorm. You also have indrafts as it's in the cumulus stage, as it's building. When it's in the mature stage, you have indrafts and downdrafts. So your indraft is bringing more air in, maybe more energy in. And then your downdraft, that's where you'd have some rain and some strong winds that can lead to erratic fire spread. And then there's like the dissipating stage as it's just downdrafts and the storm's kind of falling apart. Back to the beginning of a thunderstorm though, it's moist, warm air that's being lifted up. Two of the most common ways that happens in California is with a cold front, and you can get a lot of lightning with these kind of thunderstorms, where you have cold, dense air moving in, so then the warm, moist air is lifted up as that cold, dense air moves in below it, and then you get your row of thunderstorms along that cold front. And then with thunder, you can get some lightning. Now, where we see a lot of our lightning in California, though, is in the southeastern deserts, and then up in the higher elevations, and especially in the Sierra. The reason for that is what's called orographic lifting. So you have some air, it's moving in, it can't go through the mountains, so it's lifted up, and then cools, condenses, forms your cloud, forms your thunderstorm, you get some lightning. So that is why most of the time when you have lightning fires, they're up in the higher elevations. It's because that's where the thunderstorms are. Now, with the thunderstorm forming, you might start to wonder, okay, where's this lightning actually coming from? Like, what is the science behind lightning? So I'll simplify it. If you think of that towering cloud that we were talking about, kind of has the anvil shape. On the top of that cloud, you're going to have positive charges accumulating. On the bottom of that cloud, you're going to have negative charges accumulating. Could get into the science, but not going to, just because I don't exactly remember. I remember teaching that when I was lecturing at San Jose State, but it's not coming to my mind right now. But just take my word for it. You get positive charge at the top of the cloud, negative charge at the bottom. And then as that charge builds up, you can have the opposite charge, let's say on the ground, and then that can lead to a cloud-to-ground lightning strike. Now, only about a third of your lightning strikes are going to be cloud-to-ground, though. Some of them will just be within the cloud, maybe from your negative to the positive side within that cloud, or just from the cloud to the air around it. And then, further complicating matters, you can have what are called negative strikes and positive strikes. Now, at first, I'll admit I didn't know what this was. I thought, oh, maybe negative strikes is lightning strikes that don't lead to fires, and positive strikes are ones that do. But it's actually talking about where in the cloud that lightning strike originates. So, not a big surprise, but the negative strikes originate at the bottom of the cloud where you have the negative charge. And that's actually where most of your strikes are going to come from. But the positive strikes, so the ones that come out at the top of the cloud, those are going to be your most dangerous ones. They're going to be your most dangerous ones for two reasons. One, they're far more powerful. They can be 10 times as strong as your negative strikes, and they can be longer lasting. And then they can also strike 10 miles away from the cloud. So I always thought when we would see lightning, you count the seconds, and then you hear the thunder, and then you're able to do that equation to figure out how many miles away the cloud is. I always thought we did that to say, oh, it's 3 miles away, so we're actually safe right now. But apparently positive strikes can strike 10 miles away. So maybe a good rule of thumb is if there is lightning out there, just better safe than sorry. Stay inside. Getting back to kind of ignitions though. So a large percent of your fire ignitions are going to come from those strong positive strikes, even though those make up less of the strikes that are actually happening. The reason for that is they're longer lasting, they have more charge, they're more powerful. And there's lots of things that need to come together for your ignition to happen. So just because there's some heat source doesn't mean that you're going to have an ignition. Lots of things need to come together. I already mentioned them: temperature, fuel moisture, packing ratio, fuel load, and then the heat source itself. So some other heat sources you could think of, one could be a burning ember. And that's actually a good example here. You think of a burning ember, it's carried by wind, it drops down, it's trying to create a spot fire. Before that can actually turn into a spot fire, there's a few things that happen. You have what's called the preheating stage, where you go through hydration and pyrolysis. I know those sound very sciencey, but hydration is just a fancy way of saying the heat from that ember is evaporating the moisture out of the fuel. It's preheating the fuel because the fuel has to be dry before it can combust. And then pyrolysis is heating the fuels around that to their ignition temperature, and especially the gases, which makes them volatile. And then once those reach their ignition temperature, they vaporize, and then that's actually when you get into the gaseous stage, which is where you actually have flames on the fire. So then you have your flames that can move forward in the flaming front, and then afterwards you might have your smoldering stage. But the key thing I want to point out there is that during ignition, first you have to have enough heat to evaporate the moisture out of your fuel, and then you have to have enough heat to get that fuel to its ignition temperature. So that's a big part of the reason that although we may have a lot of heat sources out there, although there might be 2,600 lightning strikes, only 1.4% of those will actually lead to fires, at least according to that 2016 study in Yosemite. So, covered a lot of ground in the video today. Hopefully you learned at least one thing, something sticks with you. And I'm going to be learning a lot more as I continue to go through fire in California's ecosystems. So if you're interested in wildfire as well, you can come along this journey with me, and thanks for watching.